Okay, let's talk about nothing, and then let's talk about something, and then let's talk about primes. So nothingness is a concept that means absolutely nothing. It's in your mind what you can look at it as. Maybe it's dark space, or I don't know what you look at nothing, or clear, colorless nothingness. But in math, we have a symbol that can point to that concept that we form, and we use this symbol. It's zero, but that's what the symbol is, what we use to get across that notion or that idea of what nothing is. So 0 equals 0. And if I have 0 and I try and divide it by any number, well, because I'm starting off with nothing, and I try and divide nothing into something, if I take whatever nothing I have and I chop it up, I should still keep my nothingness. So that's this idea that no matter how I chop up nothing, I'll keep nothing. Even if I chop it up infinitely times or try and divide something into it infinitely times, I'll still have nothing because nothing will always be nothing. But you could see if this value of 0 is any other value, let's say 1, then I'll have something. Or if I put 1 here, I'll have a half. Or I put 1 here, I'll have a third. Or I put 1 here, I'll have 1 over infinity, which comes close to being nothing in the language of math, but it's still something because there was something other than the concept of nothing here. So because there's something there, I could have put 1 or I could put 5. 5 over infinity will still come close to 0. Or any number over infinity will come close to 0 unless I put the concept of infinity over infinity. And if infinity was exactly the same as infinity, then the concept would say, okay, infinity over infinity, well, that equals 1. And that's where we get to unity. So 1 is the whole concept of everything. I could say 1 equals 1, or I could say 1 over 1 equals 1. When I put 1 into 1 exactly one time, I'll get 1. Or if I divide 1 by itself, I'll get 1 because I never touched 1 in the first place. It just remains itself. If this is an object and I put it back into itself, or it keeps as itself, it retains its unity. But if I have two objects like a sun and then a sun and a moon, this little dot would be the moon, then now if I have this two suns and this, I'm going to end up with, well, I'll have the one concept, which could either cancel out or I could call it 1. But then I'll have that extra moon on the top that I don't have on the bottom, so I'll be left with something else. This could also here, the same concept. I'll be left with, well, this will be 1, but then I'll get that extra squiggly thing. So it'll be 1 plus squiggly thing. Or if I put this sun and a squiggly thing that's that long over that sun and that squiggly thing that's that long, well, these two suns and the parts of the squiggly lines that are different will cancel out. And I'll be left with the extra squiggly over here. So I could call all the other stuff 1 and the extra squiggly, because this squiggly is shorter than that squiggly, will be whatever extra I have. So if I have 2 over 2, it's equal to 1. Or 3 over 3, it's equal to 1. Or 4 over 4 equals 1 because unity is preserved. I'll take this and this and this and this, and 2 into 2 and it'll stay 1. Or 3 into 3 and it'll stay 1. Or 4 into 4, it'll stay 1. But for any other value except for that, like if I put 2 and 2 and then I have that extra little thing, then I'll get whatever value plus that extra thing. So I'll get 1 plus whatever extra I am. Only when these two values are exactly the same will I keep unity preserved. Whether I use these symbols of numbers or these symbols that are other types of symbols, it doesn't matter. The concept is the same, that one means complete unity. These are just other symbols that we use, but I could use suns, I could use moons, I could use stars, I could use elephants or tomatoes. Bottom line is, if there's anything extra, then it's not unity. It could be this extra little squiggle or whatever have you. Doesn't matter. We're using these numbers because that's what we use. There are symbols, but we could have used any symbol we want. It's the language that we created. So here's another special case. So if I have 1 and I divide it by nothingness, well, it could be infinity, because no matter how many times I put nothingness, how am I ever going to create something out of nothing? This is kind of like what this language is saying. So you could say, okay, well, if I keep putting nothing in infinitely times, I'll get something back, which shouldn't really be true, but I don't know, if you want to make it in your mind that way, then you can. Or you could just say, well, that doesn't make sense. I'm going to say that it's undefined, that there's no way if I put blackness into blackness, how am I going to get a pizza pie if I keep, or an apple of 1 if I keep doing that? So it's up to your interpretation. Again, this is just the language. We're making this language, and then we're taking a vote on who says that this language is right, and then that's how we create mathematics. There is no right and wrong. It's by consensus. These numbers are growing. As we need more language, we create it. Ones, zeros, millions, imaginary numbers, summation numbers, integrals, doesn't matter. So here I want to go into primes and show what they really mean. So prime numbers are really just showing what unity is. And it's a definition that we use, and prime is just, if I have a number, it's only going to be divisible by the number 1 and itself. That's the definition of a prime that we use. And it could only happen one time. So if I use the number 1, for example, well, 1 used to be considered a prime, but now they don't want to consider it a prime anymore, and we'll see why here, because it doesn't fit the definition the way we're interpreting the definition, which is, if I have 1, then sure, 1 goes into 1 one time and it retains unity. But let's say I take another 1 and then I put it into 1, and I take another 1 and I put it into 1, and I take another 1 and I put it into 1. I could still retain unity. So by definition, because I could do it more than once, they're saying that 1's not a prime, but that's just, a definition. If I put 1 into 1, I get 1. If I put 2 into 2, I get 1. 3 into 3, I get 1. 4 into 4, I get 1. Or infinity into infinity, if I keep infinity the same value, it's 1. 1 meaning unity. Now let's look at 2. Well, 2 is 1, 2, and here is 2 is considered a prime number, because if I put 1 into 2, it works. I get 2 over 1. And if I get 2 and I put 2 into 2, I'll get 2 into 2. And I'll keep 1 as the answer. But you see, if I keep going and I go 2 over 3, I'll get 2/3. Or 2 over 4, I'll get 2/4. Now I have less than 1 as I go past the number 2. And because of the definition of what a prime is, it's no longer just itself and divided by 1. So 2 is prime when we stay at 2 over 1 and 2 over 2. Let's see number 3. So 3 is prime because 3 over 3 is 1. And 3 over 2 is a fraction, so that doesn't count as being prime. And 3 over 1, well, it's divided by 1, and it's 3. And if I continue past 3, I'll get a fraction, 3 over 4, or I'll get 3 over 6. So the fractions are not in the definition of prime, so they're not included. Only in the definition. So it's best to just start at the end where we have unity 3 over 3 and I have 1. And what other numbers? Are there any other numbers that will work in between? No, only when I get back to 1 will it work, because in between I get a fraction and that doesn't count in the definition of what a prime is. If I go to 4, let's start at the end. Well, 4 over 4, it works because I have unity. 4 over 4 is 1. If I go 4 over 3, I get a fraction. Or if I go 4 over 5, I get a fraction. So that doesn't count. So to keep it, so is 4 prime? Well, let's see. So the problem is if I go back to the next whole number of 4 over 2, now there's two ways of representing this concept, because 4 over 2 is really the same thing as 2, because here is unity, 4 goes into 4, and here 2 goes into 4 2 times. So this is another way of expressing unity, is if I take this term and I take it twice, I could get back to there. Or I could take this term 4 times, which is just 1 itself, and get back to there. That's why this number is 4 equals 2 times 2, and 4 equals 2 times 2. So because of the definition of prime, this number is not prime because there's another way besides this to get back to unity. If we go to 5, we'll start with 5, which is over 5, which is unity, which is 1. But then all other things, we're getting fractions. 5 over 4. If I went on this side, I get 5 over 6. That doesn't work. That's a fraction. So where do I not get a fraction? Well, I get it no fraction back at 5 over 1. So the only way to get to 5 over 5 is 1. Or I could take 5 unit 1s to get to 5 over 5. For 6, it's the same thing. Start at unity. 6 over 6 is 1. 6 over 5 is a fraction. 6 over 4 is a fraction. 6 over 3 is 2. So I could say, okay, well, 3 is now my value of 1. So if I take 3 2 times, I'll get back my 6 over 6. Or if I take 2 3 times, I'll get back my 6 over 6. So according to the definition of prime, this is not a prime because there's another way back to that. All we're doing is we're creating a definition. These are fractions, so we're saying that that doesn't work. But if we have an entity that does exactly the same, then there's different ways of getting back to 6 over 6. I could either take this number 1 6 times, or I could take this 2 and do it 3 times, or I could take this 3 and implement it twice to get back to there. So there's other ways before here to get to here. Whereas with the prime number, the only way to get back to that unit is to get back utilizing the single units. So these are like simpler ways. If I define my number 1 as a 3, then I'd only need 2 of these number 1s to get back my whole. Or if I define this as a number 1, this 2, then I only need 3 of these units to get back my whole. Because, this is the same thing as, 3 over 1. So 3 over 1, well, times 2 will give you 6. Or this is the same thing as 2. So 2 times 3 will give you 6. So this is what prime numbers are saying. Same thing with 7 is prime because it's only whole when it's 7 over 7. All other values, 7 over 6, 7 over 5, we're getting fractions, fractions, fractions. So, and here with 8, what happens with 8? Well, 8 over 8 is wholeness, and we'll work backwards, and then we get 8 over 4 is 2. So that there's another way of getting to there. So it's not going to be prime because I could say, okay, 4 is now our number 1. So if I take 2 of these 4s together, I'll make 8 of 8. 8 over 3, it won't work because it's not in the definition. And 8 over 2 works. Is another way of getting back, because if I use these two, well, if I take it 4 times, I'll get back to 8 over 8. Same thing with 9. 9's not a prime because 9 over 9, with the definition, okay, then they're fraction, 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 fraction. But then when I get to 9 over 3, then I get something. Whereas 9 over 4, if I try that, I'll get 1 left over. But when I get 9 over 3, it works into that. 3, 3, and 3 makes 9 perfectly. So 9 could be written more simply as 3 times 3. Or, 3 times 3 will give you back to that. So working backwards, we could see what primes are saying. When I go to 10, 10 over 10 is unity. If I did 10 over 11, it's not unity anymore. Well, and then I'll work back from my number 10. So I'm starting 10 over 10, which is 1. 10 over 9, and then 10 over 8, 10 over 7, 10 over 6. 10 over 5 is the same thing as 2. So another way to get back to there would be 5 times 2. Or 2 times 5. So 10's not a prime because there's other ways of getting back to the wholeness. 11, well, by definition, none of these work because they're all going to be fractions. I'll have leftovers. So 11's a prime. 12, well, 12 over 12 is unity. What other ways can I recreate unity is the question. Using whole number concepts. That's the definition of prime. Well, this is going to be fraction, 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 fraction. And here is the same thing as 2. So if I take this 6 times, I'll get back to that. Or if I take that concept 3 times, I'll get back to that. Or that 4 times, I'll get back to that. Or that 2 times, I'll get back to that. So that's what a prime number is. It's a definition. And what these points are, the prime numbers, are just by the definition. We're not allowing anything that's fractionated to enter into our equation. We're saying prime numbers need to meet the following criteria. That's why we're finding our prime numbers. So even though these numbers all exist in the 11 range, they don't fall under our definition of what a prime is, which is divisible by 1 and itself. Because this one has other divisors, it's not within the definition, so it's excluded. So because it didn't fit our definition, which is what we're doing here, we're defining what it is. It's not a prime. So a prime is unity only at the value itself. And then as I go back for the numbers earlier, it can't be fractionated. And then here we are at 1. So basically, there's no magic here. We made a rule. We set the definition of prime. And we said only natural number values, no fraction. And the question is, what values are unity preserved at? Well, to be prime, it has to only be preserved at the last value and at the value of 1. So all primes are all made up of the little ones. Like I could also say, well, 12 times 1 equals 12. So by definition, the primes are indivisible according to the rules that we set up. That's what prime is. Meaning no fractions allowed up to that number, given the definition. But like I said, all the primes will be divisible by 1 because 1 is the unit of our language. So because 1 is going to make up every number there is, then of course 1 is going to be the hydrogen atom of numbers. And then how many hydrogen atoms make up each number is kind of up to us. And how we want to arrange that is also up to us. We developed the system. So because infinite numbers is in the language, then we have to have infinite primes, because even though it's going to become rarer and rarer as we ascend up the line, because there'll be more and more combinations to occur that can potentially recreate these ratios, like 12 over 12. Well, now I have all these combinations beforehand. But because we have an infinite system, there has to be infinite primes, because if we have infinite numbers that we can count to, we just create more numbers to find our next prime. So a highest number can never be counted. We just need to make more and more numbers. We started off with millions and billions and trillions, and then we go to powers or whatever we need to do, and eventually we'll find the next one, because we can just keep counting until we'll get to the next one, which I don't know what they're up to right now, but they'll keep counting until they find that next condition to be met, the definition to be defined. So all we're proving here is our own rules and ideas with our own symbols and our own definitions. Nothing else is being proven here. We set up the rules. We said that there's no fractions allowed, that we're trying to show what values of unity are preserved utilizing this language. And that's what we're proving here. And if you are going to say that there is God, then that means that God is complete unity, because that's what prime numbers is showing us. And that's the non-dual state, complete unity, that God is unknowable, and it's the state of non-duality that we're really proving here, is that it's infinite, but it's unity. And that's what prime numbers are showing. Infinite unity. Meaning that if I define this as symbol, this whole thing as a pizza pie, as representing everything, then it could either be 1 or infinity or whatever I want it to be, but it represents everything. So how we chop it up, that's up to us, and that's our language of math. So we're not proving God, but it is showing that God is infinite and God is complete unity, and that any separations that we're making with numbers or what have you are our own creations, our own language. We're just chopping up an infinite into mental concepts or a language or what have you. But it's all a unity, and it's an infinite unity, and what we want to call that infinite unity, whether we want to call it God or universe or universes or the Tao or whatever names you want to come up with it, that's what we're proving here. Because we're just chopping it up the way we want to. And the language evolves according to the consensus of mathematicians that say, okay, let's create a new number or a new concept. We'll call it imaginary, or we'll call it 0 or 1 or a million. But that's all we're doing, is creating more names and more concepts. And that's mathematics, a language. And I thank you for your time, and have a great day.